and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. Today's market expects electrical and electronic systems to deliver constant improvements in energy efficiency. Converters, inverters, and power supplies of all kinds have to demonstrate that their energy losses are getting lower all the time, and where possible, they need to function without the need for cooling. Not only that, but they are expected to be small and lightweight too. The very promising and commercially already enabled way is to use wide-bandgap materials in power semiconductors, that is silicon carbide and gallium nitride. WEN is a company that specializes in silicon carbide-based power electronics. Its expertise in silicon carbide puts it in the perfect position to give us exactly the right information about the energy-saving potential of power electronics made from this material. On that note, I'd like to welcome Jan Huyink. Jan is Technical Marketing Manager at WEN. Hi, Jan.
Hi, good morning.
Jan, given that WEN is still a young company, I have to ask, how's business?
Well, business has gone very well over the past years. We had a year-on-year turnover growth, and last year we even achieved our highest market share so far.
Jan, have you benefited directly from the current debate surrounding climate protection?
Yes, definitely. Our company has 4 main market segments that we target, and these are consumer electronics, big data servers, renewable energy like photovoltaic inverters, and automotive, especially electrical vehicles. And the last 2, renewable energy and automotive, are definitely part of the climate protection discussion. And with our applications for these segments, we can contribute to that.
Jan, staying in the context of climate change and cutting down on energy usage, how important do you think that SiC power electronics are in that particular context?
Okay, silicon carbide is used a lot and will be used even more in electrical vehicle chargers and onboard chargers. And silicon carbide can actually enable lower power losses. But silicon carbide parts can also contribute to lower power losses in the drive chain. And silicon carbide can be used in energy storage systems, like you could have solar power and you produce the power during the day, and then this power is stored in batteries, and then it can be used later, like in the night, to charge your car. In the future, we also want to be active in wind power, but we are not quite there yet because we would need higher voltage components. And in photovoltaic, silicon carbide MOSFETs and diodes enable higher switching frequencies and thus can lead to higher efficiencies.
Well, let's stick to the mechanisms that, wide bandgap materials, SiC and GaN components in particular, achieve such a high level of energy efficiency. What are other mechanisms that help them to achieve that?
Well, actually, if we look at efficiency, we say, okay, we want to minimize losses. And in any power electronics application, there is always your conduction losses and switching losses. Now, silicon carbide as a semiconductor material is a so-called wide-bandgap material. This means silicon carbide is very suitable for fast switching, hard switching. And to give you an example, in the past, you could do a power factor correction, PFC application, with a switching speed of, for instance, 20 kilohertz, using an IGBT as a switch and a silicon diode for the diode. But with silicon carbide, you could increase that switching speed to 100 kilohertz using a silicon carbide MOSFET as a switch and silicon carbide diode. If you do that, because of the much faster switching, you will have lower switching losses. And silicon carbide, for instance, also enables totem pole PFC. For conduction losses, we do 2 things. We have made our 6th generation of Schottky diodes, silicon carbide Schottky diodes, and the 6th generation is optimized for low VF. When the diodes have a lower VF, you subsequently have also lower conduction losses. And for the MOSFETs, we have achieved quite a low RDS(on), and RDS(on) is directly proportional to conduction losses in MOSFETs. So both the diode and MOSFET, we have a very good performance for both switching and conduction losses. Furthermore, I'd like to say that silicon carbide as a material has a low thermal resistance. This means that the heat that you generate flows away easily into the heatsink or into the PCB if you have an SMD package. And in this way, you have lower temperatures. And another benefit is lower EMI because there is less ringing in switching applications if you use silicon carbide.
What voltage ranges are especially suited to SiC and GaN solutions?
This is an interesting question. So silicon carbide is especially good for the higher voltages. Our company has silicon carbide diodes at 650 and 1200 volts and silicon carbide MOSFETs at 1200 volts and 1700 volts. To give an example, power factor correction, you can do a single or three-phase power factor correction. This is really a high voltage application because internally you have a high V bus, and the 1700 volt MOSFET is used as a switch in an auxiliary power supply for the high side MOSFET in, for instance, a PV inverter. In our roadmap, we also have 3.3 kilovolt MOSFETs that we hope to do within a few years. And this is a voltage that is suitable in, for instance, the power grid power supply for high-speed trains. This kind of applications at the moment still use a lot of IGBT, but we think in the future 3.3 kilovolt MOSFETs could take over that business. Also in very high voltage applications, I'd like to mention wind energy. Also here, high voltages are used and high voltage silicon carbide MOSFET and diode are needed. And also here we hope to have the right parts within a few years for wind energy.
Jan, you already touched up on SiC Schottky diodes and on SiC MOSFETs. I'd like to deconstruct that a little and focus on particular aspects there. So WEN started out with SiC Schottky diodes, and in 2021, your company was one of the first to launch the sixth generation of this diode. Why does this product in particular make it easier for designers to meet today's and tomorrow's energy efficiency standards?
Silicon carbide is a wide-bandgap material, as I already said. So this means it is excellent for very, very fast switching. Diodes are switching very fast. The MOSFETs, you can make them switch very, very fast. But on the diode, if we look at the diode only, the VF of a silicon carbide diode initially was not so much better than the VF of a silicon diode. So what we did is we made a new generation of silicon carbide diodes in which we changed the Schottky metal. So we took a different metal as a Schottky metal. Doing that, we lowered the VF of the diode by about 0.25 volt, so 0.25 volts. And subsequently, you will have lower conduction losses in the application because the VF of the diode is lower. I'd like to mention that if you do this, if you make VF lower, you will pay a little bit with leakage current. So there will be higher leakage. And in our benchmark studies, we were quite happy to find that for the same lowering of VF, we actually have better leakage figures than some of our competitors. So the sixth generation worked out really well for us.
Moving from the SiC Schottky diodes to the SiC MOSFETs that you recently introduced, what was the reason for expanding your range of SiC solutions to include SiC MOSFETs? And how do you view the market for them?
Yes, SiC MOSFETs are very important to have in our portfolio. I already mentioned the four main segments that we want to be active in, and SiC MOSFETs are needed a lot in those applications like switch mode power supply, uninterruptible power supply, EV chargers, onboard chargers, and PV inverters. And there's always diodes and switches in such applications. Until we had the MOSFET, we only had the diode. Now we also have the MOSFET, so we can give the complete package of silicon carbide products, both switches, so MOSFETs and diodes, to the market. And we think this market will grow a lot. Also, our own sales in silicon carbide has grown a lot in the past years. And we are very confident that the market will grow more because the silicon carbide products will enable the customers to switch faster, use smaller passive components, lower cost passive components like inductors, transformers, capacitors, and reach higher efficiency levels and lower EMI, electromagnetic interference.
Jan, SiC MOSFETs can be manufactured using either planar or trench technology. Could you explain to us what the difference between them is?
Yes, the planar technology for producing MOSFETs is the traditional way of doing it. And for planar, the gate is actually on top of the material. When you do trench technology, you kind of dig into the semiconductor material, in this case, silicon carbide, and the gate is actually lowered into the semiconductor material, and that's why you call it trench.
And Jan, why did you opt for that type of product engineering?
Yes, the planar technology for MOSFETs is easier for manufacturing in the wafer fab. And also because these were our first MOSFETs, we chose to go for the more mature planar process. So our first parts came out very, very well. And we think if you look at datasheet parameters, they are as good as parts that are made in trench technology. Having said that, in the future, definitely we also want to go for trench technology for our MOSFETs.
Packaging is always a very important issue. What trends do you see affecting discrete power components in terms of packaging?
Yes, that's a good question. Packages are very important. If you want to make a good power semiconductor device, you need to have a good silicon and you need to have a good package. So currently, we have all the discrete packages that you can find out there in the market. We have in our portfolio. For the MOSFET, we also have the 4-pin TO247 package with the Kelvin source. So this means the 4-pin package will have better switching behavior, lower ringing, and a lower EON. That's the energy to turn on the MOSFET. WIN is also making an important step now where we are going for modules. So we are going to have our own module factory, and modules, including silicon carbide dies inside, will be very important in our portfolio in the near future.
So Jan, this has been very dense in terms of information and ground that we've covered in terms of SiC and SiC power components. Now I'd love to know when and how you, on a personal level, developed your individual passion for technology.
I need to think now. An unexpected question. When I was a teenager, I was given an old radio with vacuum tubes inside. And I was very happy with my radio. And I was just flabbergasted about the fact that the voices came out of that loudspeaker. And I was listening to the BBC. And I just could not imagine how this would work. It was a wonder to me. Electronics became a hobby of mine. And I started studying electronic engineering. And in the beginning of my career, I indeed worked in telecommunications. And later I moved to the world of power electronics. And here I am in WIN Semiconductors answering questions in a podcast about silicon carbide components.
And we are very grateful for you sharing all the details, all the information that you have with us and with our audience, and also your personal origin story in terms of where your passion for technology comes from. So thank you, Jan, for the insights that you've shared with us today.
It's been a pleasure. Thank you.
Dear listeners, if you'd like to get in touch with Jan, feel free to reach out to him on LinkedIn. You can also subscribe to the WIN company page on LinkedIn. So in order to find Jan on LinkedIn, his name is spelled Jan, Jan, and then Huijink. WIN is spelled WEEN on LinkedIn. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Thank you all for listening.